This is fundamental problem 8 from chapter 14. If the force F is equal to 10 times S in newtons, where S is in meters, and the contact surface between the block and the ground is smooth, meaning there's no friction, determine the power of force F when S is equal to 5 meters. When S is equal to 0, the 20 kilogram block is moving with a velocity of 1 meter per second to the right. We have S here, and the force is acting to the right. We want to find the power of force F. For that, we use equation 14-10, and the power is the force dotted with the velocity. So we are going to need to find the velocity when S is equal to 5 meters. We can find the force when S is equal to 5 meters just by using the equation here. So in order to do this, I'm going to use the work-energy relationship that I have here, but in this case, the height of the box is not changing, so we can ignore mgh1 and mgh2 since mgh2 minus mgh1 just gives us 0. There are no springs in this problem, so this equation reduces to 1/2 mv1 squared plus the integral of f other dotted with dr, and that's equal to 1/2 mv2 squared. So I know that the initial velocity is 1 meter per second, and the mass of the crate is 20 kilograms. So this is 1/2 times 20 times 1 squared, which is just 10, plus the integral of the other forces. So let's take a look at the free body diagram in this case. We have this force, which is equal to 10s, acting to the right, and of course I have a force of gravity acting downwards and a normal force acting upwards, but because the displacement is to the right, the dot product between the normal force and the displacement is 0, so that doesn't contribute at all to the work done, and the force of gravity doesn't either because it is perpendicular to the displacement, but I don't really even need to think about that because I already considered the gravitational potential energy. So the force and the displacement are acting in the same direction, so the dot product here will be positive, and the surface is smooth, so there's no friction to consider here. So I have the integral of 10s, and recall that the magnitude of the vector dr is ds, so this is 10s ds. I'm starting at 0 and going to 5, and that is equal to 1/2 times the mass, which is 20, times v2, which will be the velocity when s is equal to 5 meters, which is what I am looking for. So we already said this first term here is just equal to 10. Then I do the integral of 10s with respect to s, and that is 1/2 times 10s squared evaluated from 0 to 5, and then half of 20 is 10, so this is 10 times v2 squared, and I want to find what v2 is. Half of 10 is 5. Putting in my limits of integration, that's 5 squared minus 0, and that's equal to 10 times v2 squared. And so I have 10 plus 5 times 25 is equal to 10 times v2 squared. So v2 is equal to 10 plus 125 divided by 10, and then take the square root. And that gives me 3.67 meters per second, and the velocity should be in the positive direction. So then when I go and do the dot product here, because the velocity is pointing in the same direction as the force, I get the power is equal to the force, which, because we're looking when s is equal to 5 meters, the force is equal to 50 newtons. So this is 50 newtons times 3.67 meters per second. That gives me 180 184. A Newton times a meter is a joule, and a joule per second is a watt. And 184 watts is the answer to fundamental problem 8.